Assalamualaikum warahmatullahi wabarakatuh to our lecturer Sir Tuan Syekh Ahmad Izzadin Syekh Muhammad Ghazali. So in this video, we would like to present and explain more of the chapter 4, which is the compounds with metal carbon sigma bonds. Before we proceed more on this video, we will introduce to you each one of our group members. This is Nur Azreen Binti Azizan, Mimi Wahidah Binti Radzi, and Nurul Aine Binti Musa.
Assalamualaikum and hi, my name is Azreen Binti Azizan. So for this CHM676 assignment, I will elaborate about chapter 4, which is compound with metal carbon alpha bonds. So first of all, we start off with there are three type of group that can metal carbon alpha bond can form, which is first aryls, acyl, and also alkyls. As you can see in the slide here, the next to the name is the example of one of the example for aryls, acyl, and also alkyls. In beta hydride elimination mechanism, they have two type of group that can take place. First, metal alkyls, and the second one is metal aryls. So first, I would like to explain about metal alkyls. In metal alkyls, there are two type mechanism that take place. First, a vacant coordination site on the metal, and the second one is a vacant orbital on the metal. For a vacant coordination site on the metal, is a stable transition metal alkyls and works as follow.
Is to essentially go to 18 electrons. So if you go to a transition metal alkyl complex that has 18 electrons, essentially what you've done when you get to 18 electrons is you said all the orbitals are filled. Okay? So if all the orbitals are filled with electrons, then there's no way that the alkyl group can come round in a beta-agostic interaction and bind to the transition metal center. And so if you have a complex like this is an 18 electron complex and it's perfectly stable.
And for a vacant orbital on the metal is which only available in transition metals that not main groups of metals, which are stable main group alkalis containing beta hydride such as Grignard reagent can be found. And it works as follows.
Instability of transition metal alkyls is frequently the following reaction. If you start off with a titanium dialkyl species, so this is a titanium dialkyl species, diethyl titanium, doesn't really matter at this stage what the other R ligands are. If you have a compound like that, then what you've got are two ethyl ligands. Now, ethyl ligand bound, so we've drawn out one of these ethyl ligands, titanium CH2, CH3. Now, what you have, if you have a CH3, is what we call a beta hydrogen. So this is the alpha carbon, this is the beta carbon, this is a hydrogen bonded to the beta carbon. Now, this hydrogen bonded to a beta carbon can interact with the transition metal center. Now, this is possible in transition metal centers and not possible in main group complexes. The reason is because transition metal complexes have additional vacant orbitals. So there's an orbital that's not being used in tetraethyl titanium, and that orbital can coordinate this beta hydride. The next step is more than coordination. It's actually the beta hydrogen migrating to the transition metal center. What we're doing is forming a new titanium hydride bond and liberating an equivalent of alkene. So the first step in the decomposition of one of these titanium alkyls is the formation of a titanium hydride and an equivalent of alkene. When you have a hydrido-alkane complex.
Now I will proceed with the second type of group, which is metal aryls. This metal aryls does not undergo beta elimination decomposition easily because first the metal carbon alpha, carbon beta, and also hydrogen beta must be in coplanar, which is it is very difficult to achieve because theory of strain. And the next reason is because it will destroy aromaticity, which is not desirable, and is related to the stability of the ring. So the example from metal ions is phenyls, as you can see here, and also THF, or known as tetrahydrofuran, and many more other complexes.
Aryl ligands. Aryl ligands are relatively strong anionic 2-electron donors, like alkyls. Since they cannot easily be hydride, eliminate metal aryls are relatively stable. Aryls do have the potential for both p donation and p back bonding through the filled aryl p orbitals and empty p antibonding orbitals.
As in the previous video, it already explained about metal ions, and it also stated that metal ions undergo two types of equation, which is first pi donation, and the next one is pi star back donation. So here the example of how this pi donation and pi star back donation works.
Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone, especially to our lecturer, Sir CHM676 Syekh Muhammad Ghazali. First of all, my name is Wahidah Binti Radzi, and I am from class AS 202 5 and 1. So today I would like to continue with our presentation with the title, The Compounds with Multiple Metal Carbon Bonds. So basically there are two types of multiple metal carbon bonds, which are metal carbon double bonds M double bond C and metal carbon triple bonds M triple bond C. So but as for my part, I will only explain the metal carbon double bond, and later Aine will explain more about metal carbon triple bond. So in metal carbon double bonds, there are two main types of metal carbon carbon complexes, which consists of Fischer type carbon complex that we call as carbene, and short type carbon complex that also known as alkylidene complex. Now, firstly, Fischer type carbon complex. The Fischer carbon complex found on electron rich and low oxidation state metal complex, which usually will be found in the middle to late transition metals that contain pi acceptor ligand. So for example here, iron, molybdenum, and also chromium. So the Fischer carbon complex is usually weak at back donating, but the stability can be enhanced with the presence of highly electronegative heteroatoms. The example of heteroatoms is such as oxygen, nitrogen, and also sulfur. So these heteroatoms on the alpha carbon will allow to draw a resonance structure, and it also tend to participate in the pi back donating with d orbital on the metal and p orbitals on the carbon. So as you can see from the picture above here, there is a lone pair that is donated from a carbon to an empty d orbital on the metal. So it has been highlighted with the red color, and then another lone pair is donated from pi back donate metal to a vacant pz orbital on carbon with the blue highlighted color. However, there is a competition for this vacant orbital by the lone pairs itself on the heteroatoms, which consistent with the second resonance structure. The bonding is most likely close to carbon monoxide, CO bond, and good electrons for back donation with good pi acceptor. So these carbene ligands are usually thought of as neutral species. Next is short type carbon complex. It is also known as alkylidene complex. Unlike in Fischer carbon complex, which it is electrophilic in nature, the short type alkylidene complex is a nucleophilic, and its back bonding metal is strong, and it contributes the sigma donation from the ligand to the metal. So this type of complexes has high valence oxidation state in early transition metal, which contain good sigma or pi donor ligands in the complex. So its carbon-carbon is destabilized with heteroatoms, but it attached directly with hydrogen or alkyl. These complexes are composed with two covalent bond interactions. One electron will donate to the sigma bond from each metal and each carbene. So for this slide, I have summarized the differences between two types of carbene complex, Fischer and Schroth type alkylidene complex, according to their characteristics. Before I end this video, I will show you one video that I obtained from the YouTube, which maybe could be more understand on it, and that is all from me. Thank you.
The bonding is based on sigma type electron donation of the filled lone pair orbital of the carbene atom to an empty metal d orbital and pi electron back bonding of a filled metal d orbital to the empty p orbital on carbon. Now we see the resonance structure of Fischer carbene. Here the substituents are heteroatoms. The ligands attached to the metal atom are pi acceptor metal ligands, so it withdraws electrons towards itself. The pi electron moves from carbon to metal, so carbon atom acquires positive charge. To balance this, the heteroatom donate electrons to carbon. It gets this resonance structure. Now, this carbon is more electrophilic in nature. The metal atoms are low oxidation state in Fischer carbene. The substituents, the X and Y, are pi down substituents. Bonding in this complex can be viewed as the coupling of triplet state metal and triplet carbene. Next we see the shark carbene. Here the X and Y are hydrogen or alkyl group. The ligands Ln attached to the metal atoms are not pi acceptor ligands. So the electron density around the carbon is more. So it acts as nucleophilic in nature. The metal atom in shark carbene is high oxidation state. The substituents are non-pi down substituents.
Assalamualaikum and hi. My name is Nurul and Binti Musa, and now I'm going to talk about the Fischer type carbene complexes. Most Fischer carbene complexes are stable to air and water and to dilute acids and bases. It is more stable than its Schroth type counterpart. Presence of the highly electronegative atoms such as O, N, and S attach to the carbene carbon because they can participate in the pi bonding. Results in a delocalized 3-atom pi system involving the d orbital on the metal, p orbital on the C, and p orbital on the electronegative atom. The localized 3-atom system provides extra stability to the bonding pi electron pair than would a simple metal to carbon pi bond. Next, for the N111C carbene and alkylidene complexes, bonds are present in the carbene and alkylidene complexes, which are related to carbene and alkylidene complexes respectively. They can be obtained from the carbenes through removal of the heteroatom substituent. Schroth type alkylidene complex alpha hydrogen is removed to prepare an alkylidene complex. The function of phenyl trimethyl in the example is to increase steric crowding around the metal center, which is eventually being eliminated. This is the summary of the MC sigma bond types. Bond type for alkyl, aryl, carbene, alkylidene, carbene, and alkylidene. That's all for chapter 4. Thank you.